Hello everyone. In this video, I'm explaining Poisson's distribution. See, in the earlier video, I had explained what is a binomial distribution and when this binomial distribution is applied. Suppose if you have a random experiment that has finite number of trials and the probability of success P and probability of failure that do not differ much, in that case we can always go with binomial distribution. But that is not always the case. You may have random experiment where you may not get finite number of trials and there is a lot of difference between probability of success and failure. So in such cases we go with the Poisson distribution. So the conditions are here: when probability of success is very small and number of trials may not be known, either it is infinite or there is no particular finite count for the trials. In such cases we go with the new distribution called as Poisson's distribution. For example, number of accidents occurring at a particular spot on a road every day is a rare event. It's an example for a random experiment where the distribution to be applied is Poisson, because in such cases we usually apply Poisson distribution because we don't know the particular count of accidents. It is a random event and the probability of success, probability of accidents occurring at a particular spot on a road is very small. It depends. In some of the days it may be more and some of the days it may be less. It is totally a random event. So in such cases we don't know number of trials as well as the probability of success becomes very small. We go with the Poisson distribution. So in Poisson distribution, our interest lies in number of occurrences and not in non-occurrences. We are not bothered much about probability of failure here. We are bothered about probability of success. See, for example, how many printing mistakes are there on each page of a book. Here we are concentrated to count the number of printing mistakes and we are not sitting and counting number of words without printing mistake. We don't want those words without printing mistake. We want just those words with the printing mistakes. Similarly, counting number of defects per item in production, in any production company. Suppose if you want to find out number of defects per item, then we are concentrating only on this defected items. We don't concentrate on non-defected items. So this is the basic criteria under Poisson's distribution. See here, this Poisson distribution can be viewed as a limiting case of binomial distribution under the following conditions. Here, number of trials is indefinitely large, as n tends to infinity, you can write, and p, the probability of success for each trial is very small, that is p tends to 0. NP is a finite quantity. We name it as lambda. This lambda plays an important role in Poisson distribution. This is a parameter lambda. It is a finite quantity. N into P. This value is called as lambda. Therefore, mathematically, we define a Poisson distribution as a random variable x is said to follow Poisson distribution if it assumes indefinite number of non-negative integer values, means success values x equals 0 success, 1 success, 2 success. We don't know because number of trials is not known. So it takes indefinite number of positive as well as 0 integer values and its probability mass function, because it is again a discrete probability distribution. We are studying now discrete probability distribution. So its probability mass function is given by, see, this is the formula, e power minus lambda into lambda power x by x factorial. X is 0, 1, 2 and so on. Lambda is always positive real value and 0 elsewhere. In all other cases it is 0. For all these values x equal to 0, 1, 2 and so on, the probability mass function is given by e power minus lambda into lambda power x by x factorial, where e is the base of natural logarithm. Its approximate value rounded off to 4 decimal places is given by 2.7183. See, if x follows Poisson distribution with parameter lambda, then we write it as x following the Poisson distribution p of lambda. And one more property is that if x and y are two independent Poisson variates with parameters lambda 1 and lambda 2 respectively, then x plus y is also Poisson variate with parameter lambda 1 plus lambda 2. This is called as additive property of Poisson distribution. The condition is x and y must be independent Poisson variates. Then only this gets satisfied. So this is all about Poisson distribution. So when to apply this Poisson distribution, that you should know, and what is the probability mass function of Poisson distribution. Now let us know about moments of Poisson distribution. So two types of moments about origin and moments about mean. These are central moments. So moments about origin, mu1 dash is equal to, you get it as lambda. I'll directly give you the formula. The method how it arrives is given in the textbook. Mu2 dash equal to lambda square plus lambda. Mu3 dash is lambda cube plus 3 lambda square plus lambda. Mu4 dash is this value. So out of which the first moment about origin is the mean. So this gives you mean equal to lambda. Here you have to remember the formula for mean equal to lambda. That helps you to find out the parameter lambda of Poisson's distribution. Lambda is calculated using this mean. Now moments about mean, central moments, mu1 is first central moment is always 0, mu2 equal to lambda, again this also comes to be lambda, but we know that second central moment is variance, so variance is equal to lambda. Mu3 also equal to lambda, so this is the speciality of Poisson distribution, and mu4 is 3 lambda square plus lambda. So you have to remember these central moments important, and mean and variance. So in Poisson's distribution, mean and variance is given by lambda, as well as the third central moment is also equal to lambda. So now how to measure skewness and kurtosis for Poisson's distribution. So beta 1 we know mu3 square by mu2 square. Using this formula we will get lambda square by lambda cube. Mu3 is lambda, mu2 is also lambda. So this gives you 1 by lambda. So gamma 1 equal to square root of beta 1, which is equal to 1 by square root of lambda. Similarly, beta 2 is this formula. As applying on this formula, we will get beta 2 as 3 plus 1 by lambda, gamma 2 as 1 by lambda. So based on these two, gamma 1 is positive. This gives you the gamma 1 is used to measure the skewness. This Poisson's distribution is always positively skewed because gamma 1 is positive. Negative means negatively skewed. But this lambda be specified always greater than 0. Therefore, 1 by root of lambda also becomes greater than 0. So it is always positive. Hence, it is positively skewed. Similarly, gamma 2 also becomes positive because we specified lambda is a parameter which is always greater than 0. Hence, gamma 2 also becomes greater than 0. The curve becomes leptokurtic. Kurtosis is measured here. It is a leptokurtic curve. So for Poisson's distribution, you have to remember these things. It is always positively skewed and it is a leptokurtic. Distribution curve is leptokurtic. And for a Poisson distribution, mean equal to variance equal to the third central moment, that is all equal to the value lambda, the parameter lambda, which is always positive. Let us solve some problems to understand the concept of Poisson distribution. Now see the first problem. It is known that the number of heavy trucks arriving at a railway station follows the Poisson distribution. It is given in the question. If the average number of truck arrivals during a specified period of an hour is 2, find the probabilities that during a given hour no heavy truck arrive, at least 2 trucks will arrive. This you have to find out now. So it is a Poisson distribution. So what is probability mass function of a Poisson distribution? It is equal to e power minus lambda into lambda power x divided by x factorial. So based on this probability mass function, now we want lambda. So how to calculate lambda? You know that moments about origin as well as moments about the mean. So based on that, you got mean equal to lambda. Okay, so here they have given the average number of truck arrivals during a specified period of an hour is 2. So average equal to 2. So that is nothing but lambda equal to 2. Therefore, now this probability mass function becomes e power minus 2 2 to the power x divided by x factorial. X can take values from 0, 1, 2 and so on. What is the first question? No heavy truck arrive. So x equal to 0. Probability of success here. Success, number of success equal to 0. So it is e power minus 2 into 2 to the power 0 divided by 0 factorial. 2 to the power 0 is 1, 0 factorial is always 1. So it is e power minus 2, 1 by e square. You can use the scientific calculator to calculate e value 2.7135 that I told you. It's a square. Then 1 by this value. So it comes out to be 0.1353. You can take log table as well to or statistical table to find the value of e square. Next, what is the second question? At least 2 trucks will arrive. So probability at least means minimum 2, maybe more than 2. More than 2 means how many? We don't know. Number of trials not given. For a Poisson distribution, it may not be known. So we want to find out probability of x greater than or equal to 2. Number of trucks arriving more than 2, at least 2 or more than 2. So for that what we do is 1 minus probability of x equal to 0, 1. Okay, we can do it in this way also, which we have done for binomial distribution also. X equal to 2, 3, 4, 5, up to what? We don't know. Until where we don't know. So that's why we can find it as a, because total probability of any probability distribution is always 1. So 1 minus not included here, which are the not included values 0 and 1. So this is equal to 1 minus probability of at x equal to 0 means e power minus 2 into 2 to the power 0 by 0 factorial. Just now we calculated. And here e power minus 2 into 2 to the power 1 by 1 factorial. So this is equal to 1 minus this value is 0.1353, and after simplifying this comes out to be 2 by e square. This is 2 by e square. You need to simplify this value. So after simplification, this comes out to be 4059. So this is equal to 0.5941. This is the probability of at least 2 trucks will arrive. So this is how we solve a problem related to Poisson distribution using its probability mass function, where lambda is calculated using the concept of mean, because mean is always equal to lambda in a Poisson distribution. Here mean is given, average number of truck arrivals. Next question. If the probability that an individual suffers a bad reaction from an injection of a given serum is 0.001, determine probability that out of 1500 individuals, exactly 3 and more than 2 individuals suffer from bad reaction. See, here nowhere it is Poisson distribution directly given. But look at the probability of success. It is 0.001, very, very small. So here P equal to 0.001. Probability of success is 0.001. And number of trials also mentioned here, n equal to 1500. Though there are number of trials mentioned here, as the probability of success is very, very small, we can take this as a limiting case of binomial distribution, because limiting case of binomial distribution is n tends to infinity, p tends to 0, then it becomes Poisson's distribution. Number of trials also more here, and probability of success is very less, and np is finite quantity, I told you, and it is denoted as lambda. So in this case, in such cases, lambda is calculated using this formula, lambda equal to np. We have to consider binomial distribution only, and we have to take it as a limiting case of binomial distribution to apply the Poisson distribution. Therefore, now let us find out lambda. Earlier, lambda was taken as mean, but nowhere mean is given, so we should make use of a formula of mean in of binomial distribution. In binomial distribution, mean is given by n into p. You make use of that formula. So lambda equal to n into b by considering this as a limiting case of a binomial distribution. So n is 1500 into 0.001, which is equal to 1.5. So we got lambda. Now probability mass function of Poisson distribution is x equal to x e to the power minus lambda, lambda power x by x factorial. This is e power minus 1.5 into 1.5 to the power x by x factorial. So first question is exactly 3. So x equal to 3, correct? No. So e to the power minus 1.5 into 1.5 to the power 3 divided by 3 factorial. We have to simplify this. So this comes out to be 0.2231. This value into 1.5 whole cube is 3.375 divided by 3 factorial is 6. So 0.1255. Next, second question is more than 2 individuals suffer from bad reaction. Probability x is greater than 2. So greater than 2 up to 1500. You can't sit and calculate all these. So we can go with 1 minus missing value. P of x equal to 0, 1, 2. Greater than 2 means starting from 3, 4. So the values missing here are 0, 1, 2. We have to find out for those. So 1 minus probability of x equal to 0 means e power minus 1.5 into 1.5 power 0 by 0 factorial plus e power minus 1.5 into 1.5 to the power 1 by 1 factorial plus e power minus 1.5 into 1.5 to the power 2 by 2 factorial. Let us simplify this. You can take e to the power minus 1.5 outside, then this value is 1 plus this is 1.5 and this is 1.5 square by 2, that is 2.25 by 2. So this is equal to 1 minus this value is 3.625 into 0.2231. So finally we will arrive at the value 0.1913. So this is the final answer. See the third one. For a Poisson distribution, it is given that P of x equal to 1 equal to P of x equal to 2. Find the value of mean of the distribution. So mean is equal to nothing but lambda. You have to find the value of lambda. Hence find x equal to 0 and probability at x equal to 4. So let us do that. Here given P of x equal to 1 equal to P of x equal to 2. These two probability values are same. So e power minus lambda into lambda power x means 1 by 1 factorial. E power minus lambda into lambda power x means 2 here by 2 factorial. So this implies lambda equal to lambda square by 2. So lambda square minus 2 lambda equal to 0. Lambda into lambda minus 2 equal to 0. Lambda equal to either 0 or lambda equal to 2. But lambda equal to 0, it is not possible because our lambda is always greater than 0. Lambda is always greater than 0 because lambda equal to np. If lambda becomes 0, np becomes 0. Either n should be 0 or probability should be 0. So Poisson distribution doesn't exist. So lambda greater than 0 implies lambda equal to 2. So this is equal to mean. We got the value of mean. Mean equal to 2. Next we want to get P of x equal to 0. Simple. E to the power minus lambda into lambda we got 2 to the power 0 divided by 0 factorial. Here it is 2. So this is e power minus 2, that is 1 by e square. So 1 by e square value is 0.1353. Next we want probability at x equal to 4. So e to the power minus 2 into 2 to the power 4 divided by 4 factorial. So it is e power minus 2 into 16 divided by 24. So upon simplification we will get 2 by 3 into 0.1353, which is equal to 0.0902. This is the probability of the random variable at x equal to 4. Next problem, if x and y are two independent Poisson variates. So this is given. You have to make use of additive property having means 1 and 2 respectively. So lambda 1 equal to 1 and lambda 2 equal to 2, because for a Poisson distribution mean equal to lambda. So that's why I have taken lambda 1 is 1, lambda 2 equal to 2. Therefore, P of x plus y also, this x plus y also follows a Poisson distribution with parameters lambda 1 plus lambda 2. So that is nothing but 2 plus 1, 3. So you can name this x plus y as w. So w is a random variate, Poisson variate, which follows the Poisson distribution with parameter equal to 3, lambda equal to 3. So p of w here. Now w is less than 2. So probability of w less than 2 means w equal to 0, 1. Here probability of w equal to 0 plus probability of w equal to 1. So Poisson distribution, this w also follows Poisson's distribution. So e power minus 3 to the power 0 by 0 factorial plus e power minus 3 to the power 1 by 1 factor. Why 3? Because lambda is 3 for this. So this gives you 0.0498 into 1 plus 3. So this is the value of e power minus 3. This is 1, 3 power 0, 3 power 1 is 3. So finally 0.1992. This is the answer. Now let us see how to fit Poisson distribution to the given data. See, to fit a Poisson distribution to the observed data means the observed data will be given to you. You have to fit Poisson distribution to that observed data, and you have to calculate theoretical frequencies, and you have to check whether theoretical frequencies and observed frequencies will match or not. See, first step is to do that. Recurrence formula for probabilities of Poisson distribution, you have to find it out. That is given by p of x plus 1 equal to lambda by x plus 1 into p of x. Next, second step is you have to get the Poisson frequency distribution. So Poisson frequency distribution is, see, in case if an experiment satisfying requirements of Poisson distribution is repeated n times, then expected frequency of getting x successes is given by f of x, means it is the frequency function, frequency distribution. P of x means probability distribution. Now we have to find out f of x frequency distribution because the experiment is repeated n times. So it is given by f of x equal to capital N into p of x at x equal to x. So you have to multiply the probability value for that x successes by capital N, number of times it is repeated. So apply this probability mass function, you will get f of x, f of 0, f of 1. This way you have to calculate. Step 3 is process of fitting Poisson distribution. So main intention is to fit Poisson distribution to the given data. When the Poisson distribution gets fitted to the given data, if you obtain the mean of that distribution and if you equate that mean to lambda, because in a Poisson distribution mean is always equal to lambda. If you equate that to lambda, then it becomes Poisson distribution, fitting that to Poisson distribution. If you equate that equal to np, then it becomes a binomial distribution, as we have done in the previous case of binomial distribution. One set of data is given to you, you have to fit a particular distribution for that data. If it is Poisson distribution, then equate the mean to lambda. So lambda equal to the obtained mean. Then you have to use the recurrence formula to get p of 0, probabilities p of 0, p of 1, p of 2 and so on. Then get expected frequencies or theoretical frequencies, that is given by f of 1 equal to n into p of 1, next n into p of 2, like that. Let us illustrate this with an example. First example, the following data gives frequencies of aircraft accidents experienced by 2480 pilots during a certain period. So number of accidents and their frequencies given. You have to fit a Poisson distribution and calculate the theoretical frequencies. So first let us fit a probability distribution to this data. Later we will find out the theoretical frequencies. Then you match theoretical frequencies with the observed frequencies. So first what you should do, first step is you have to find the mean of this distribution and we have to equate mean to lambda because we are fitting Poisson distribution. So right now number of accidents, that is the variate, random variate, which is x. Then frequencies is f. So x is 0, 1, 2, 3, 4, 5. 0 accidents. 1970 flights had 0 accidents. 1 accident, 422 flights. 2 accidents, 71. Then 3, 13. Then 4, 3. Then 5 accidents, only 1 flight experienced this. This was the given data, observed data. We have to fit Poisson's distribution into this data. So first what you should do, first let us find out the mean. So to find the mean of a frequency distribution, what we should do, find fx, then find capital N, that is nothing but f, sum of f, summation of the frequencies comes out to be 2480, which that should be same as 2480 total flights. And now let us find out fx. Here it is 0 first case. Next this is 422, this is 142, 13 threes 39, then 12, then 5. Sum of all these, that gives you 620. Now I want mean equal to summation of fi xi divided by summation of f. So 620 divided by 2480. So this comes out to be 0.25. We want to fit a Poisson distribution. So take this as lambda. This is the first step in fitting Poisson distribution. Once you have fit the Poisson distribution, now get the probability distribution. Probability distribution is obtained by the recurrence relation. What is the recurrence relation? P of x plus 1 equal to lambda by x plus 1 into P of x. So lambda is 0.25 divided by x plus 1 into P of x. Now we have to formulate a table for this, finding the probability distribution. Now we just fitted Poisson distribution to this data by taking mean as lambda. Now we have to fit the probability distribution. Let us do that by writing the tabular column. See, these are the columns, number of accidents. Then we want this value, lambda by x plus 1, that is the recurrence relation. Then for that you have to multiply this P of x to get the value of P of 0, P of 1, like that. Then expected frequencies. F of x is n into P of x. So x takes the value 0, 1, 2, 3, 4, 5. So first for 0. So here you have to substitute lambda is 0.25 divided by 0 plus 1, that is 0.25 by 1, which is equal to 0.25. Now I want first case P of 0. So P of 0 equal to P of x at x equal to 0. What is the formula? E power minus lambda into lambda power 0 divided by 0 factorial. So that comes out to be e to the power minus lambda value is 0.25. So this is equal to 0.7788. Now f of 0 equal to, you will get this value 0.7788 into 2480. So that gives you 1931. Okay, this is f of 0. Next for f of 1. So put x equal to 1 now. 0.25 divided by 1 plus 1, that is 2. So this gives you 0.125. Now I want P of 1. P of 1 equal to. So now make use of a recurrence relation. Only for this you have to make use of the formula, the probability mass function formula. Now for P of 1, what is the recurrence relation? That is lambda by x plus 1 into P of 0. Correct? Now this was the recurrence relation. So what is the recurrence relation? Recurrence relation is P of x plus 1 equal to lambda by P of x plus 1 into P of x. Now to get P of 1, I need lambda by 0 plus 1 into P of 0. So what is lambda by 0 plus 1? That is this value. So 0.25. So 0.25 into this value, P of 0, 0.7788. So that gives you 0.1947. So f of 1 equal to n into this value, which comes out to be 483. Next 2. 0.25 divided by 2 plus 1, 0.25 by 3, 0.0833. So P of 2 equal to, as per the recurrence relation, put x equal to 1. So lambda by 1 plus 1. That is, you have to make use of these two values. So which is P of 2 equal to 0.125 into 0.1947. So that gives you 0.0243. So that's why it is recurrence relation, because we need to use the previous values. So f of 2 equal to this value into 2480. So that gives you 60. Next, for 3.25 divided by 3 plus 1. This will be used for the next one, but we are calculating it here. This is 0.0625. So P of 3 equal to, you have to multiply these two now, 0.0833 into 0.0243. So this gives you 0.0020. Now multiply this with the 2480. So that gives you 4.96 approximately, that is 5. Here also this gives you actually 60.3. We will round it off to 60. Next, 4.25 divided by 4 plus 1, that is 0.05. Now P of 4, we need to multiply these two values, 0.0625 into 0.0020. That gives you 0.0001. So 0.001 into 2480, you will get 0.248. So you can approximate that to 0. Next, fifth one, for value 5, 0.25 divided by 5 plus 1. So this gives you 0.0417. Next, P of 5 we want 0.05. This into this 0.0001, which gives you 0.00005. This into 2480, which is approximately equal to 0. So these are expected frequencies or theoretical frequencies, whereas we got the observed frequencies as, see, 1970, first one. Here we got 1970, then 422, 71, 13, 3 and 1. But in last two cases we got approximately 0. Here it is 5, here it is 60, 483, 1931. So this is how to fit the Poisson distribution for the given data and to find the expected frequencies or theoretical frequencies for the given data. This is called as fitting of Poisson distribution. I hope you understood the concept of Poisson distribution. Thank you for watching.